Okay, so sigma and pi bonding. When we look at covalent bonding with Lewis structures, we really simplify the model of electron configuration that we've learned previously. So when you draw a molecule of hydrogen, you usually think of hydrogen with a dot and this hydrogen with a dot, and then you can put them together and show that they have a pair of electrons shared between them, and usually then we draw it as a line. But if we want to try to take this model of covalent bonding and actually align it with what we've learned about orbitals, then we have to incorporate what are known as sigma and pi bonds. So on the right here is a simple model, kind of like our Lewis structure, of what a covalent bond is. We've previously defined it as the electrostatic attraction between two nuclei and the shared electron pairs between them. And so we've got our positively charged nuclei, and we've got the electron pairs here, or there's one electron pair, sorry, the electrons in between them, and the nuclei are attracting them, they're pulling them towards themselves, and that's what holds the two nuclei together. Okay, so that's how we've looked at covalent bonds previously. But if we try to now align that with our atomic orbitals, if we think about hydrogen, we would have said hydrogen's configuration is 1s1, and the other hydrogen has a configuration of 1s1. We would have drawn box and arrow diagrams kind of like this to represent that one electron. And if we drew their s orbitals, we would have drawn something that's kind of like a sphere. So we have all these different ways of kind of thinking about electrons, different models to think about electrons. So when you have atomic orbitals like this and a covalent bond is formed, the idea is that the atomic orbitals overlap with one another and essentially create one larger orbital. So if I think about these two s orbitals and they come together, I get something like the picture down here, where there's two s orbitals, they start to merge with one another, and they create one larger orbital around those two atoms, and mostly the electron density would be in between the two nuclei. And so remember that these orbitals are really visual representations of these wave equations that represent where we're most likely to find electrons. And you can actually add waves together. When you add waves together, you get a combination of constructive and destructive interference. So you literally can add waves together, and so you literally can add these orbitals together, because orbitals are just the visual representation of these wave functions. But that all sounds a bit abstract. What we need to know for the IB is that when we have covalent bonding, we're going to have atomic orbitals overlapping to create new kinds of orbitals that we call bonding orbitals. And so the simplest kind is the sigma bond. And the sigma bond involves two orbitals. They can be any kind of orbital. When they simply merge and overlap in a head-on way, so that's one way you'll see it described on the exam or on a mark scheme, is that it's head-on overlap. And what results is you get an orbital that is symmetric around the bond axis. So the bond axis would be, if you drew a line between the two nuclei, that would be the bond axis. And so this orbital is symmetric around that bond axis. And the electron density is mostly in between the two bonding nuclei. So most of the electron density is in between the two nuclei. So that's what a sigma bond is. Sigma bonds can happen between s orbitals with other s orbitals. They can happen if p orbitals were to overlap this way head on, so the two ends of the p orbitals are directly overlapping. They can happen between s and p orbitals. So sigma bonds can happen between any kind of orbital. Because otherwise you might get the misunderstanding that sigma is only between s, because that's sort of the first example that we use, but actually sigma bonds can happen between any kinds of orbitals. And so we've got these orbitals merging together to create the sigma bond here, the merged orbital. And if you thought of it as a box, then the two electrons that we had here have now created that nice shared pair and that full first energy level. But really, for you, you need to know the definition of a sigma bond, head-on or axial overlap, and electron density between the two nuclei. They can happen between all types of orbitals. And when you're looking at a Lewis structure, anytime you see a single bond between atoms, that bond is a sigma bond. This is the first kind of bond that forms between atoms. So when you have methane, methane has 4 single bonds. Every single one of these is a sigma bond. So this, we would say, has 4 sigma bonds. And I'm using the Greek sigma symbol here, the Greek letter there. Now, if you have something with a double bond, so let's say you have CO2, you have carbon dioxide. So it has 4 bonds, but they're both double bonds. In a situation like this, the 2 of these bonds are sigma bonds. So you can think of it as the first bond between each. There's always, when you have multiple bonds between atoms, one of them is always sigma. So the ones in purple, let's say those ones are sigma bonds. There's no distinction in a Lewis structure between a sigma bond and the other kind of bond, which I'm about to talk about. So there are 2 sigma bonds here. But if you think about the carbon overlapping with the oxygen, if they have electron density right between them with the first sigma bond, and then you have the other oxygen over here, and there's electron density with the second sigma bond there, then where do the second bonds go? Because we know electrons repel each other, and so if you have 2 electron pairs between each carbon and each oxygen, they each need to sort of find their own location to exist in, where they're not going to repel each other so much. And so the idea behind where the next bonds go is with something called a pi bond. So a pi bond is the other kind of bond you need to know about, and it only happens between p orbitals. So sigma bonds happen between all types of orbitals, but pi bonds can only happen between p orbitals. And so pi bonds form from what they call sideways overlap of parallel p orbitals. And the electron density is actually not between the 2 nuclei, but instead it is above and below the bond axis, just like a p orbital. So if you think of this p orbital here, the p orbital is this propeller shape, and the nucleus was actually here in the middle. So in a p orbital, the electron density was above and below the nucleus. And so when you have a pi bond, you have essentially 2 p orbitals lined up with each other, parallel like, and then they're going to overlap. And so the p orbitals are going to merge together. They're going to merge together on the top, and they're going to merge together on the bottom. And so you end up with a pi bond. And so a pi bond is basically just like an extended p orbital. It looks like just a wider p orbital. So there's still no electron density in between the nuclei, or where the nuclei are, and all the electron density is above and below the 2 nuclei. So the 2 nuclei are here. So that's the definition of a pi bond. And that allows us to have extra bonds in between these atoms, and they can occupy a different space from the sigma bonds. So, for example, in carbon dioxide, you can have carbon has a p orbital here, and so this oxygen must also have a p orbital that's parallel, and so that allows overlap to happen above and overlap to happen below. And so all of what I've just drawn in orange, that is one pi bond. Okay, I know it's in 2 places, it's above and below, but it just counts as one pi bond. Just like a p orbital is in 2 places, right? It's above and below, but it just counts as one orbital. So this is one pi bond. So then where's this other, so that's the one in orange, and then I'll draw it in, let's say, I'll draw it in purple. No, I'll draw it in green. Okay, this last bond, where does that go? Well, remember that p orbitals are at 90 degrees from each other. So if the orange bond is straight up and down, then the green one can exist into and out of the page, into and out of the board or my iPad here. And so I'll try to draw that. It's a little hard with only 2 dimensions, but there is another p orbital. There's another way for the p orbitals to be parallel, and it's kind of sticking in and out of the board. You might think of it as like the z axis in math class, the one that would stick in and out of the page. And so there's another orientation for this other pi bond to go. And so you can now see that every bond sort of has its own space to occupy in between the atoms and around the atoms, so that the electron pairs, which repel each other, all have their own region and they're not all right on top of each other. And so when you look at a Lewis structure, the one bond between atoms is always a sigma bond. If there are any extra bonds, then those extra bonds are always pi bonds. And so if we think of just a couple more examples, and this is just an illustration down here of a combination of sigma bonds between carbon atoms, and then in the green it shows a pi bond that's happening above and below. So yeah, if we look at this Lewis structure for ethene, if I was asked to count all the sigma and pi bonds, then really the only one to worry about is the double bond. So one of those bonds is sigma and one of them will be pi. All the other bonds are single bonds, and so I know those are sigma bonds. So I would say there's one pi bond in this molecule, there's one extra bond, and there's 5 sigma bonds. If I were to draw instead something with a triple bond, like ethine, then the single bonds are sigma, and one of the bonds between the atoms is sigma, and so in this one there are 3 sigma bonds, and that leaves, there must be 2 pi bonds. So the extra bonds here are pi bonds. So you're expected to be able to define sigma and pi bonds, know what kind of orbitals they can happen between, and then be able to look at Lewis structures and count the numbers of sigma and pi bonds. You are not expected to draw anything that looks like this or that looks like this. You are welcome to, but it's not a requirement on any question that you have to draw these sort of cartoony orbital-like drawings. It's just a way to try to visualize and explain how the sigma and pi bonds fit together in a molecule.